Hey everyone, and welcome to today's Explainer. I am so incredibly excited you're joining me because today we're going on a seriously fascinating journey. We are going to zoom all the way down into the microscopic building blocks of the universe, the tiny, ancient particles that literally make up absolutely everything around you. And then we're going to connect those tiny particles directly to their massive, real-world impacts on our lives today. So get ready to see the world in a completely different way. To kick things off, let's think about this. What actually makes gold different from iron? I mean, they're both metals, right? But gold has this beautiful, shiny yellow appearance, and it's highly unreactive. It basically stays pristine for thousands of years. Iron, on the other hand, looks silvery and, as we all know, easily rust the second you leave it out in the rain. So how can they look and behave so differently if they're fundamentally made out of the exact same microscopic stuff? Well, the answer lies hidden deep within their atoms. For a really long time, people thought of atoms as these tiny, solid little marbles. In fact, the word atom itself comes from the ancient Greek word atomos, which literally translates to unsplittable. But science eventually shattered that historical illusion for us. Atoms are absolutely not solid, and they certainly aren't unsplittable. Instead, as we're about to see, there is this bustling, dynamic, beautifully organized world happening inside every single atom. To give you a sense of scale here, 100,000 times. The radius of an atom is approximately 100,000 times larger than the radius of its very center, the nucleus. To kind of visualize this, imagine the nucleus of an atom is the size of a standard football, just resting on the ground. The closest outer edge of that atom, it would be about 5 kilometers away. That is roughly the length of 50 football fields laid end to end. So an atom is actually almost entirely empty space. So here is the roadmap for our explainer today. 1. Anatomy of an atom. 2. Elements, compounds, and mixtures. 3. The isotope plot twist. And 4. Real-world isotope power. Let's dive right in.
Section 1. Anatomy of an atom. The bustling world inside.
Okay, remember our question about gold and iron? The reason those two metals are so radically different is simply that their atoms contain different numbers of subatomic particles. So let's meet them. First up, the proton. Now, the proton is proactive. It carries a positive electrical charge of +1 and sits right in the middle of things, inside the nucleus. Next is the neutron. And just like it sounds, it's totally neutral. No electrical charge at all. It's just hanging out in the nucleus alongside the protons, keeping everything together. Both of these guys have a relative mass of 1. And finally, we have the electron, carrying a negative charge of -1 and orbiting in the outer shells far, far away from the center. Now, hold on a second, because this is wild. An electron is staggeringly light. It has a relative mass of just 1/1840th of a proton. Just imagine that for a second. You would need almost 2,000 electrons to equal the mass of a single proton. This means practically the entire mass of an atom is packed into that tiny, dense nucleus, right in the center, while these almost completely weightless electrons are just speeding around the vast empty space outside it. And those electrons, they don't just float around randomly. They are highly organized into specific energy levels or shells whizzing around the core. We call this the electronic configuration. The electrons always fill the lowest energy levels first. Those are the ones closest to the nucleus. The first inner shell is small. It can only hold a maximum of 2 electrons. Once that one is full, electrons move to the second shell, which can hold up to 8. And the third shell generally holds another 8. Understanding this 2-8-8 rule is absolutely crucial. It's the key to understanding why elements react with one another to form the entire world around us. Section 2. Elements, compounds, and mixtures. Building the macro world. All right, so how do these individual microscopic atoms actually combine to make up the physical matter that you can see, touch, and breathe? Let's start with compounds. A compound is a pure substance containing 2 or more elements that are chemically bonded together in a strict, fixed ratio. The perfect example of this is water, H2O. Every single molecule of water, literally no matter where you find it in the universe, has exactly 2 hydrogen atoms chemically bonded to exactly 1 oxygen atom. That fixed 2-to-1 ratio, that is exactly what makes it a compound. But of course, not everything out there is chemically bonded. We just learned that compounds have a fixed ratio and actually require chemical reactions to separate them. Mixtures, on the other hand, are basically just physical blends. There's no fixed ratio and 0 chemical bonding occurs. Think of the air you're breathing right now. It's a mixture of nitrogen, oxygen, and carbon dioxide. Or think of brass, which is an alloy mixture of copper and zinc. Because they are just mixed together physically, the individual components retain their own unique properties and can be separated by physical means, like boiling or filtering. To ground this abstract chemistry in everyday life, just consider emulsion paint or even a glass of milk. You might look at them and think they are pure substances, but they're actually really complex physical mixtures. Specifically, they're types of mixtures called sols and emulsions, where different substances are suspended in one another, but they are never chemically joined.
Section 3. The isotope plot twist. Anomalies in the atom.
Okay, we've built the world up, but now it's time for a bit of a plot twist. Remember earlier when I said that an element is defined by its atoms? Well, despite what we just learned, it turns out that not all atoms of the exact same element are perfectly identical. And this brings us to isotopes. Isotopes are atoms of the exact same element that have the same proton number, but a completely different number of neutrons. Remember, the number of protons determines what the element actually is. 6 protons will always be carbon. But neutrons carry no charge, so an atom can gain or lose a neutron, which changes its total mass, but its chemical behavior remains exactly the same. Let's look at the simplest element out there, hydrogen, as a prime example. Hydrogen actually comes in 3 natural variations. Most hydrogen is hydrogen 1, which just has a proton and 0 neutrons. But sometimes nature sneaks a neutron in there, creating hydrogen 2. And very rarely it sneaks in 2 neutrons, making hydrogen 3. They are all hydrogen, they all act like hydrogen, but they have slightly different masses. And this tiny atomic anomaly leads to incredibly fascinating real-world effects. If you take that slightly heavier isotope, hydrogen 2, which is also known as deuterium, and make water out of it, you get what's called heavy water. It looks and tastes like regular water, but because it's slightly denser, at high levels it physically acts differently. It can actually slow down cell functions in living things. Just think about that. A single extra neutron fundamentally shifts how a substance interacts with biology.
Section 4. Real-world isotope power, from anomalies to applications.
So why does all this matter? Well, the crucial point is how these microscopic atomic variations aren't just chemistry trivia. They result in massive, real-world applications. Harnessing the power of isotopes for human energy and medicines starts with radioisotopes. While some isotopes are stable, others really aren't. A radioisotope is an isotope whose nucleus has so many extra neutrons that it becomes unstable. Imagine lugging around a backpack that is just way too heavy. Eventually, you're going to drop something. These unstable atoms break up spontaneously, and when they do, they release powerful energy and radiation in a process we call radioactivity. And the crazy part is, we can actually capture that breaking energy. Uranium-235 is a radioisotope of uranium. It's slightly heavier than standard uranium, making it highly unstable. When humans intentionally facilitate the breakup of these tiny, unstable uranium-235 atoms in a highly controlled environment, the energy released is so profound that it boils water to turn massive turbines. We literally generate enough electricity to power entire modern cities through nuclear power stations, all from this process. And it's not just energy. There's an incredible medical side to this too. Inside a modern radiotherapy machine, we use a radioisotope called cobalt-60. As the unstable cobalt-60 atom spontaneously breaks down, it emits high-energy gamma rays. In modern medicine, doctors carefully direct this precise beam of radiation right into a patient's body to target and kill tumor tissues, ultimately saving lives. All of this incredible, life-saving technology is rooted entirely in understanding the extra neutrons tucked inside a single atom. We have covered some truly incredible ground in this explainer today. We unlocked the bustling anatomy of the atom. We learned exactly how elements chemically bond into compounds or physically mix to create our material world. And we saw how the tiny neutron anomalies of isotopes can power entire cities and heal the sick. So I want to leave you with this final, provocative thought. If everything you love, fear, and experience is ultimately just a specific arrangement of these tiny, ancient subatomic particles, what else is waiting to be built? Thank you so much for exploring with me today. Stay curious, keep learning, and I'll catch you in the next explainer.